Hi, everyone. I want to talk to you about covalent bonding, which is section 7.2 from chapter 7. And covalent bonding is different from ionic bonding in that covalent bonds are about sharing electrons. That's our key word for covalent bonding. They share electrons. So when we talk about covalent bonding, we have previously talked about ways to predict if something was covalent. And pretty much the trick we said was it's covalent bonding if it's nonmetals bonded with other nonmetals, or sometimes nonmetals bonded with metalloids. What we want to look at, though, is the idea that Lewis theory says everything wants 8 valence electrons because that means all of the valence orbitals are full for the most part, with exceptions. The sharing of electrons is not the transfer, but the sharing of electrons is how nonmetals can achieve their octets. So we are sharing electrons to get an octet. And when we share electrons, we are going to see them drawn into structures, much like we drew Lewis symbols with dots. We will see dots drawn in what are known as Lewis structures. I'm not going to talk about Lewis structures in this video. I have another video where we're going to talk about putting the structure of a compound together, but you should be used to seeing the dots from learning about Lewis symbols. I'll come back to these, what's bonding and non-bonding in a minute. What I want to discuss is this term electronegativity first, because electronegativity is going to be what truly determines if the compound is covalent or ionic. Not actually non-metal, non-metal, metal, non-metal, although that is the trend, that is what we see. It's really about this property called electronegativity. Electronegativity is a periodic trend that you should have studied in the previous chapter, but just as a refresher, electronegativity, I symbolize just capital E, capital N for electronegativity, and it is the pull or the attraction, but I like to say the word pull. It's the pull an atom has for shared electrons in a bond. So we're talking about a bond. A bond is going to be 2 electrons. And kind of specifically, we're looking at this for, covalent bonds, right? Okay, a covalent bond is when 2 electrons are shared. And in fact, what we call that is a single covalent bond, okay? A single covalent bond has 2 shared electrons. And in some drawings, you might see those 2 electrons. So here I'm going to do element X and element Y, okay? Here's an electron from one, here's an electron from the other, and they are shared between the 2 atoms. You might see the dots like this, but more commonly what you're going to see when we're talking about this single covalent bond is we draw a single line. You can also have double and triple covalent bonds, and those share 4 electrons and 6 electrons respectively. In drawings, you will see these shared electrons. again as lines. So that 2 lines together in between those atoms is a double bond. It means 4 electrons are shared. If you were thinking about dots, you might think about it like that. We typically don't do that. We draw these lines. The lines are the bonds. What are bonds? Shared electrons. The number that is shared, here I'll do X. Okay, I did X there. It doesn't matter. Whatever the 2 atoms are. The number that is shared is represented by these lines. Okay, each line is 2 electrons. Here they are. When we talk about the pull an atom has for these shared electrons, it is based on this thing called electronegativity. Those shared electrons are not necessarily shared equally. They are shared. Each atom gets to count them for itself, for its octet, but they may be actually physically closer to one atom than the other in the bond. That's the pull. What we look at is electronegativity and the trend. I do not need you to know specific values of electronegativity. We want the trend for electronegativity. If you look at a bond like a single bond between hydrogen atoms, so I have H and H. Come here. Two atoms that are identical to each other. Each atom has the same electronegativity. Doesn't matter what the number is. If they're the same element, they have the same electronegativity. That makes sense. And so that shared bond, those 2 shared electrons really truly are dead ass in the middle between the 2 atoms. All right? We have a word for that when they are shared equally. You could jot it down now, but I'll tell you more in a minute. It's called nonpolar. But when you have 2 different elements, there is a difference in this property, electronegativity. And the shared electrons in a bond are pulled closer to one atom over the other. And sometimes the difference in electronegativity is so big, like with metals and nonmetals, that you don't share anymore. You actually get electrons straight transferred over. Okay. But just looking at covalent, just looking at the sharing, here's our trend for those electronegativity values. Generally, as you move left to right, the electronegativity increases. As you move down, the electronegativity decreases. The most electronegative element is fluorine. Next is oxygen. And then actually next we say is nitrogen. So N, O, and F are the 3 most electronegative elements, with F, fluorine, being the most. Hydrogen, of course, is over here, but number-wise, it really kind of fits more over here between boron and carbon, okay? So when we have a bond and we're trying to judge, is the sharing equal or is the sharing unequal? The words that we use are polar and nonpolar. So if I have a polar covalent bond, I have 2 different elements. And yes, these should be nonmetals or maybe metalloids, okay? If it's a metal, I can tell you it's going to be ionic. It's not covalent at all. So what we want to do is just look at one bond between two elements and let's decide if it's polar. So let's do the H and the C. So if I had an H and I said C, I meant chlorine. And let's say there is a single covalent bond between them, okay? Remember, that line represents 2 electrons. Which element is more electronegative, chlorine or hydrogen? You got to think about your trend. You got to know your trend. It should be the chlorine atom. Why? Because chlorine is further to the left to the right on the periodic table. It is closer to fluorine. Any of those things will help you remember that chlorine is more electronegative than hydrogen. And so these electrons are not dead ass in the center of these 2 atoms. They are actually a little closer to the chlorine. But see, with the dots, that doesn't come across very well. It almost looks like it's not even shared with the hydrogen at all. So what we do is our single line, and then we draw special symbols on our elements. That indicate which one is the more electronegative. Because chlorine is more electronegative, the symbol that we write is this Greek letter. This is the lowercase Greek letter delta. Capital delta is the triangle. This symbol is the lowercase Greek letter delta. Do I need to draw it again? It's like a D, but it's got a little curve flare to it, okay? And in this context, delta means partially, okay? And if this is the more electronegative element, and it is pulling those shared electrons closer to its side, this is partially negative. It's not full on negative. It is not an anion. This is still sharing, so it's covalent, but this side is a little more negative than this side of the bond. And so the other side, we might draw that same delta, but with a positive sign. Okay. And one more symbol that we can draw on a bond that you'll see is what is known as a dipole moment. So I'm drawing an arrow and I point it towards the partial negative side of the bond. And then these arrows have a little tail on them, and that is the side on the partial positive, okay? What does that mean? That arrow is showing the pull, the direction of the pull, okay? That is what the arrow means. This is, again, this is known as a dipole moment. This is a force. It's something that can be calculated. You can calculate the dipole moment. We're not going to do that in this class, but it is an actual physical value. Okay. All right. That's polar covalent bonds. You should expect to have a polar covalent bond when you have 2 different elements bonded together, with an exception. And there could be other exceptions based on really looking at electronegativity values, but here's the main exception you had better know. A carbon-hydrogen bond. A carbon-hydrogen bond is not polar. There is equal sharing here. Their electronegativity values are close enough to each other that one does not pull more than the other one. They equally share. So the phrase for when equal sharing happens is nonpolar. nonpolar covalent bonds are when equal sharing is going on, and you will see this with two identical elements, or with a carbon-hydrogen bond. Okay? Nonpolar covalent. Nonpolar does not have a partial negative, partial positive side. Okay. And I think that might be it for this section. The next section is about drawing these things called Lewis structures. When I drew, or when we looked at the structure for water, as you'll practice in a video, we're going to draw the compounds and try to describe the bonding inside of it. And so you should now be able to understand in further videos, what is that's been drawn? That is what is known as a single covalent bond. The other thing you might need to know is sometimes in our structures that you'll be drawing, you will have some electrons, right? Some electrons that are not shared. They are there, as you will learn how to count that they're there. But remember, these represent shared electrons, or what we might say are bonding electrons. Okay. These dots represent what are known as lone pairs or non-bonding electrons. And you will learn how to draw these structures in another video.